Welcome back, everyone. The purpose for this video is to look at some weak acid equilibria calculations. So as a quick review, we talked in a past video where we introduced weak acid and base equilibria that we have this general reaction, right? And we are going to use this during our calculations, okay? And we're also going to use the Ka expression, where we've got the concentration of the hydronium ion, the conjugate base, all divided by the concentration of that weak acid. So in our first example, the pH of a 0.23 molar solution of hydrofluoric acid is 1.92. Determine the Ka for HF, or from hydrofluoric acid, from these data. So when we look at a problem like this, they are asking for the Ka value. Okay, and they give us the pH as well as the concentration of the acid. Now, I think it's helpful to always use that same general reaction, right, that we have. And if we're going to do that, it helps to mark out the acid that they give you and relabel that as HA. Okay, so we just generalize all acids to that same formula, and so we always write down the same reaction. And for the most part, I'm going to ignore the phases except for water, and that's just so that I know, because it's a liquid, I don't want to include it in that equilibrium expression. Okay, and so I write this reaction out so that I can form an ice table. And remember that the I stands for initial, C for change, and E for equilibrium. Okay. And because water is a liquid, we can ignore that section because we're not going to need it for the equilibrium expression. And remember that we know Ka, because we use this general reaction, will always be the hydronium ion concentration, H3O+, times A negative, which represents our conjugate base, divided by HA, which is the weak acid. Okay, and keep in mind that when we are using that Ka value and all those equilibrium, all those concentrations, know that they are at equilibrium, right? So we need to use the values from this last row, which represents the equilibrium, in that Ka expression. Okay, now the concentration that they give us starting out, right, that has to be HA at the initial value. So the initial value of our weak acid is 0.23. And because we're not changing volumes, we can use molarity for everything in our ice table. We don't have to switch to moles. And then because we're not dealing with a buffer and we haven't added any type of a salt to this reaction, then we know that we start out with 0 for our products. Okay, and because all the coefficients are 1 and we don't see any coefficients in front of any of our reactants or our products, then we know that that's going to be a change of X minus on the reactant side and plus X on the product side. And so at equilibrium for the weak acid, it's going to be 0.23 minus X, and then for both of our products, it will be X and X. Okay, so before we plug this into our Ka expression, we know that we need to know what all of those values are in order to determine Ka, right? So we need to know what that value of X is. And the best way to determine that is that they give us the pH, right? pH is equal to 1.92. And what does the pH tell us? Well, the pH tells us the concentration of the hydronium ion at equilibrium. So we can determine the value of X from that pH value, right? And so we know that the equation, the hydronium ion concentration, will be equal to 10 to the negative pH value. And so 10 to the negative 1.92. And remember that the number of digits after the decimal, that tells you the number of significant figures in the hydronium ion concentration. So we need 2 sig figs at least, but because we're not done with the problem, we do want to give us at least 3 for round off error. And just keep in mind, it will help if you note that that hydronium ion concentration, that is equal to X, right? So X is equal to 10 to the negative 1.92. Plug that into your calculator and you find that it is 0.0120. And remember, I subscript that last digit because it's not significant, but I want to carry it in my calculator or in my calculations until the end. And we don't necessarily need units for calculating Ka values, but just know that that X is going to be in units of molarity because these are concentrations. So now that I know the value of X, I can plug it into my Ka expression, right, using the fact that the hydronium ion is X, the weak base is also X, and then Ha is 0.23 minus X. And so Ka equals X times X for your two products divided by 0.23 minus X. And then plugging in the value that we have for X, right, you get the 0.012, square that, divided by 0.23 minus 0.012. Okay, if you decide to plug this into your calculator all at once, just make sure that you do put parentheses around those bottom values, okay? Otherwise, you might get a different answer. And your final answer should come out to 2 significant figures, right? We've got 2 significant figures throughout. And when you do that subtraction step, you'll find that you still have 2 sig figs. And so Ka is equal to 6.6 times 10 to the negative 4th. So just to summarize real quick, because we were given the concentration and the pH, right? So if you're given the concentration and the pH and you're asked to determine the Ka value, then you don't have to use that 5% rule. And if you need to, go back to the first video in this series, look back at that 5% rule that we talked about. But it's not necessary to use here because pH tells us the value of X. Right, and the 5% rule is all about avoiding the quadratic equation where you have to calculate the value of X based off the equilibrium expression. So if you already know what X is through the pH, then we don't need the 5% rule. Okay, and so just to summarize the steps that we did here, we use the pH to determine the value of X, and remember that's because the hydronium ion concentration at equilibrium is equal to X. Okay, so that's how we get the value of X from the pH. And then you can plug that into the ionization constant expression where X squared divided by the original concentration of that weak acid. So that should technically be, right, HA with a 0 to denote initial concentration minus X. Okay, we're going to do one more example in this video where we look at propionic acid. It's used in the manufacture of calcium, calcium propionate, a food preservative. What is the pH of a 0.698 molar solution of this acid? Okay, and so the first thing that I do is I mark out whatever acid that I have, no matter how complicated it is, and I rewrite it just as HA. Okay, and then I've got it written over here as well, so let's mark that out and generalize it to any weak acid. Okay, and by doing that, I can rewrite that equation that I've already used, HA plus liquid water yields the hydronium ion concentration plus the weak base. Okay, and I'm going to go ahead and set up my ice table as well. And mark out that liquid water because we're not going to use it in the equilibrium expression. And let's go ahead and write out that equilibrium expression just so we have it. So it's going to be the concentration of the products, right, over the concentration of that weak acid. And keeping in mind that all of this has to come from that third row, right, that equilibrium row. Okay, that's what matters to us. So they give us the original concentration of the weak acid, 0.698. And then we start out with 0 for both of our products, again, because we don't have a buffer solution, which we'll look at later. And then the change for the reactants, minus X, and plus X for the products, because all of those coefficients are 1. And so again, we get the original concentration of the acid, 6.98 or 0.698, minus X, and then on the product side we have X and X. Okay, now this time they give us the Ka value, right? So they give us the Ka value, which means we're going to need to solve for X. They don't give us the pH because the pH is what we're looking for. Right, and so if we're looking for what is the pH, remember that that's equal to the negative log of the concentration of that hydronium ion. And so that's what we need to find in order to solve for pH. And to find that, right, we look at that equilibrium expression, that's going to be equal to X. So basically pH is going to be equal to the negative log of X if we can find what X is. And so in the past we've had to probably do the quadratic equation, but here we're going to use that 5% rule and see if it works. So remember, if we assume the 5% rule, then that means that the equilibrium concentration of the weak acid, right, so that's here, 0.698 minus X, we are going to assume that that is about the same or equal to the original concentration of that weak acid. So basically remove that minus X. Okay, and we do have to check and make sure that this is acceptable. So once we find that value of X, we're going to have to calculate the percent ionization. So just if you have to, leave yourself a note that says that check that 5% rule. Okay, and we can't do that until we get that value of X. So leave yourself a note, and then let's go ahead and plug in our values for Ka. So in this Ka expression, right, we know what the value of Ka is. Ka is equal to 1.34 times 10 to the negative fifth. And that is equal to our hydronium ion concentration times the weak base, which remember both of those are just values of X. So we get X times X, and then divided by the equilibrium concentration of the weak acid, which we're going to assume is the same as the original concentration of that weak acid. And so we're going to plug that in as 0.698 and ignore the minus X part. Okay, so now we don't have to use the quadratic equation. We can simply rearrange this, move that 0.698 over, and take the square root. And so X is equal to the square root of 1.34 times 10 to the negative fifth, and multiply that by the 0.698. Okay, 3 sig figs for both of those numbers, and so for the answer, we're going to keep an extra digit until we're done. And so we get 0.00305 8. And we've got to remember what X equals, right? X is equal to the hydronium ion concentration at equilibrium, which is going to help us determine the pH. And so if we need to, we can write out here that that X is equal to the hydronium ion concentration, which is what we want. Okay, but before we plug that in and use it for the pH, let's check that 5% rule and check that percent ionization. So percent ionization, remember that is going to be equal to your concentration of the hydronium ion at equilibrium divided by the original concentration of that weak acid. And then of course multiply times 100%. Okay, so plugging that in, the X gives us our hydronium ion concentration, which is why we had to calculate it. So that's that 0.003058 divided by the original value of 0.698 and then times 100%. Okay, and we are going to find that that is 0.4% roughly. Okay, so that is significantly less than the 5% rule, and so it checks out, right? The assume 5% rule, it checks out because it is less than 5%, and so we can finish off this problem. Okay, we've got the hydronium ion concentration down here. We know that pH is equal to the negative log of that hydronium ion concentration, and so pH is equal to the negative log of 0.003058, keeping in mind that that is 3 significant figures within the logarithm, and so the final answer needs to have 3 digits after the decimal. Okay, so that comes out to be 2.515. All right. So just to summarize what we've done, if you are given the concentration and the Ka value, right? So this is different than the first example we did where they gave us the pH. So if you're given the Ka value and you're asked to determine what the pH is, then the 5% rule is necessary, okay, because we are having to calculate X from that equilibrium expression, and we can't use it from the pH value. Okay, so if the 5% rule doesn't hold up, then you have to apply the quadratic formula, and so you have to include that minus X part, and it just makes it a few extra steps. Okay, so what we did here to summarize, we took that Ka expression and we know that it's equal to X squared divided by the original concentration of the weak acid. Again, this only works if we assume the 5% rule. And then once we determine the value of X, right, so the whole purpose of using this expression is to calculate the value of X using all the other values that are given. And then we check the 5% rule by dividing X by the original concentration, make sure that that is less than 5%. And if it is, then we can use X to determine the pH, because again, X is equal to that hydronium ion concentration as long as we are looking at a weak acid. Okay, so that ends this video. In the next video, we'll look at weak bases.